For the past 3 years, the industry has concentrated on conversational chatbots. You submit a prompt, the system queries a vector database, and a large language model streams back a synthesized text response. That interaction is read-only, stateless, and sandboxed inside a single forward pass. An AI agent is an entirely different architectural paradigm. An agent is not a chatbot with extra system prompts. An agent is an autonomous software system that pairs an LLM reasoning core with stateful memory, multi-step planning, and external tools to execute end-to-end goals with real-world side effects. A chatbot explains how to resolve a database deadlock. An agent queries your live telemetry, isolates the locking transaction, writes an idempotent migration script, verifies database health metrics, and submits a pull request. Today, on day 20, we conclude phase 1 of our 100-day AI engineering series by breaking down autonomous agent loop mechanics, React patterns, deterministic tool use, model context protocol, live incident triage, and senior production best practices. At the foundation of virtually every agent runtime is the React primitive, short for reason plus act. Instead of generating an answer in a single forward pass, the agent executes an iterative 3-phase control loop. Phase 1, thought. The LLM inspects the original goal alongside the execution history, verbalizing an internal reasoning trace that decides what specific subtask needs to happen next. Phase 2, action. The model emits a deterministic command, typically a structured JSON payload targeting a specific API endpoint, database query, or sandboxed shell script. Phase 3, observation. The agent runtime intercepts the tool call, executes it in the external environment, captures the raw execution output, and appends that observation back into the model's context window. The agent then evaluates whether the goal has been achieved. If not, it executes another iteration, dynamically adjusting its next thought based on the new environment state. This loop continues until the task finishes or hits a termination boundary. How does a probabilistic, non-deterministic language model trigger deterministic software systems without crashing on syntax errors? The answer is structured function calling and constrained grammar decoding. During inference, the runtime provides the model with JSON schemas defining available tools, required parameter types, and allowed values. Modern serving engines use context-free grammars to mathematically constrain the token sampling space. During decoding, tokens that would violate the JSON schema receive a probability of negative infinity. The LLM is physically incapable of emitting invalid JSON keys, missing required fields, or outputting malformed types. Once the tool payload completes, the agent runtime intercepts the token stream, validates the payload against the schema, executes the corresponding Python method or REST endpoint, and feeds the result back into the conversation history as a structured tool message. Historically, connecting agents to external tools suffered from an M/N integration problem. Every agent framework implemented its own proprietary tool calling interface, requiring bespoke glue code for every database, API, and file system. The industry solved this with the Model Context Protocol, or MCP. If the LLM is the reasoning brain, MCP is the universal nervous system connecting it to hands and eyes. MCP standardizes 3 core primitives. First, tools, callable functions that execute actions and mutate external state, like pushing git commits or running SQL mutations. Second, resources, read-only contextual data, such as file contents, server logs, or schema definitions. Third, prompts, pre-configured workflow templates and /commands that guide agent behavior. By standardizing over lightweight, stateless JSON RPC protocols, developers build an MCP tool server once, and any compliant agent, whether running in an IDE, CLI, or cloud orchestrator, can discover and use it immediately. Let's see an autonomous agent in action on a real production incident. An alert fires. Our primary database connection pool is 98% saturated. Step 1. The agent reads the incident webhook and verbalizes a thought. Inspect active database queries. It invokes the PostgreSQL MCP tool to query pgstat activity. Step 2. The tool observation returns a long-running unindexed query on the orders table that has been holding locks for over 5 minutes. Step 3. The agent drafts a zero-downtime remediation script. Create index concurrently. It executes the script inside an isolated sandbox replica to verify syntax and execution time. Step 4. Because creating an index mutates production state, the agent reaches a human-in-the-loop gate. It posts a structured summary to the Slack incident channel with dry run telemetry. The on-call SRE clicks approve. Step 5. The agent applies the migration, verifies that connection saturation drops to 12%, and resolves the PagerDuty incident automatically. An agent's capability is bounded by how it manages state. Production agents utilize a 3-tier memory architecture. Tier 1. Working memory. This is the active context window containing system prompts, tool schemas, and immediate React step history. It is fast and volatile, requiring active context pruning to avoid token bloat. Tier 2. Thread and episodic memory. Persisted inside a state store like Redis or PostgreSQL. Every thought, action, and observation is recorded as an immutable checkpoint. If an agent crashes midway through a 30-step deployment, it resumes from its last checkpoint rather than restarting from step 1. Tier 3. Semantic long-term memory. Stored in vector databases or knowledge graphs. When an agent tackles a complex objective, it queries past runs to retrieve historical success patterns, error workarounds, and user preferences accumulated over months of operation. For complex, multi-stage workflows, naive single-step React breaks down. The model loses focus, suffers from context clutter, or spirals into repetitive loops. Production architectures employ hierarchical planning frameworks. In the plan and solve pattern, a high-level planner LLM decomposes the user's objective into a directed acyclic graph of independent subtasks. Dedicated worker agents execute each subtask in isolated context sandboxes, returning only concise summary payloads to the parent coordinator. In the Evaluator-Critic pattern, every action or code patch generated by an actor agent is passed to an independent critic model that runs automated unit tests, schema validators, or linter rules before committing changes. Decoupling high-level planning from low-level execution keeps context windows clean, reduces token costs, and drastically minimizes compounding reasoning errors. Granting autonomous agents access to real-world tools introduces serious engineering and security hazards. Hazard 1. The infinite loop. If an API returns an unexpected error format, the agent may retry identical requests indefinitely. Always enforce a hard maximum iteration threshold, token budget caps, and exponential back-off circuit breakers. Hazard 2. Indirect prompt injection. When an agent reads an untrusted web page, user ticket, or database record containing malicious instructions, those instructions can hijack the agent's internal reasoning trace. Treat all tool observations as untrusted data, sanitizing inputs before context insertion. Hazard 3. Unbounded blast radius. Never grant an agent destructive permissions without human-in-the-loop authorization. For destructive actions, like dropping database tables, transferring funds, or deploying code to production, the agent must pause, yield execution, and await signed human confirmation before proceeding. To deploy reliable agents at scale, senior engineers adhere to 6 core best practices. Rule 1. Minimize your tool surface area. Do not give an agent 50 tools at once. Give it 3 to 5 highly focused tools. Model routing accuracy degrades sharply as tool counts increase. Rule 2. Design all tools to be idempotent. If a network timeout occurs and the agent retries an action, executing that tool twice must produce the exact same outcome without creating duplicate records or charges. Rule 3. Return structured, informative errors. Never feed raw stack traces back to the LLM. Return structured JSON explaining exactly what argument failed and how to remediate it. Rule 4. Isolate read tools from write tools. Grant autonomous access to read-only replicas, but strictly gate write permissions behind authentication checks. Rule 5. Enforce token budgets per run. Cap each agent workflow to a maximum token spend and iteration limit. And Rule 6. Log full open telemetry trace spans for every thought, action, and observation so you can replay any failed execution step with complete fidelity. Do you actually need an agent? 9 out of 10 enterprise problems do not require autonomous agency. If your use case is answering questions from internal documentation, drafting email summaries, or classifying incoming support tickets, standard deterministic code paired with RAG is faster, orders of magnitude cheaper, and infinitely more reliable. Adopt an autonomous agent architecture only when the sequence of steps cannot be hard-coded in advance. The system must dynamically adapt to environment feedback, and the workflow requires multi-step interaction with external APIs. When you do build agents, standardize on a modern enterprise stack. Use LangGraph or Temporal for durable state persistence. Model Context Protocol for tool interfaces. E2B micro VMs or Docker for execution isolation. And Open Telemetry for end-to-end tracing. To summarize, chatbots talk, agents act. Chatbots operate in a single-turn conversational sandbox. Agents navigate dynamic environments using the React loop. Constrained tool calling, model context protocol, multi-tier memory, and hierarchical planning DAGs. Respect the latency, cost, and safety trade-offs. Never build an agent when a deterministic script or simple RAG pipeline will solve the problem. But when you need dynamic, multi-step problem solving, build a stateful, sandboxed, and fully observable agent architecture. This concludes Phase 1, AI Fundamentals of our 100-day AI Engineering series. Over the past 20 days, we have built a rock-solid foundation across LLM architectures, embeddings, vector databases, RAG pipelines, fine-tuning, inference engines, and autonomous agents. Tomorrow, we kick off Phase 2 with Day 21, Prompt Engineering and In-Context Learning Deep Dive. Subscribe, star the GitHub repository, and I will see you tomorrow.